Hi, in this video, we want to take a look at some of the normal distribution functions that we have in Python. All right, so once again, we're going to be using an Introduction to Statistics with Python textbook. I'm copy and pasting much of the code from that textbook, and here is the website if you want to go check it out, check out the original. Remember that the textbook is for free as being a UCF student. You just need to put in your NID and boom, you can download it. All right, so what we want to do, we want to take a look at the normal distribution functions in Python. Why is this important? All right, normal distribution tells me, gives me insight into how sample averages will behave. That's basically why it's important. Now, this does not work out 100% of the time. It's not, the vast majority of the time, the sample average will be, if I have a large enough sample. So let's say I'm going to go out, I'm going to collect 100 observations, take the average. I get another 100 observations, take the average. Get another 100 observations, take the average. Another 100, take the average. I do this over and over and over. Let's say I get, 2,000 averages total. I want to know what is the distribution of the averages. In almost every situation, you're going to have something that looks like the normal distribution as long as you have like independence and finite mean, finite variance taken care of in your sampling process. And you're sampling from the same distribution the entire time. Okay, well, what this means is that the normal distribution comes up in a lot of situations because of the sample average relationship. And so one thing that is important to us in data science is that because of this conversion from almost every single type of random variable to the normal distribution, if I'm in a situation, in certain situations, I can actually use the normal distribution to understand other distributions pretty well. And this comes up all over the place. This is super powerful, super important. And this is why you had to suffer through it in your Stat Methods 1 class back in the undergrad. All right, so now let's go ahead and import NumPy, Matplotlib, PyPlot, and SciPy stats. Now we're going to go ahead and import Seaborn. Remember, Seaborn is the way in Python to get good, beautiful, beautiful graphics. Now, what I want to do here, I want to go through and I want to generate some data. And here I can do stats.norm. I'm using standard normal, mean 0, standard deviation of 1, or variance of 1, either way. And then we're going to go through and generate some data. Now, what I want to do, I want to plot some particular aspects of this data. So something that's nice about Matplotlib is it makes it very easy to create subplots. This is probably the strongest feature of Python visualizations is the subplot aspect that I have a lot more control, and it's much easier than in SAS or in R or SPSS. So what I'm going to do, I'm going to make a subplot grid. See, I've got 3 and 2, 0, 0, and column span is 2. Go through, and I'm just going to go ahead and execute this. So first one is we're going to get the density function, the bell curve. Then we're going to get the cumulative density function. That's going to be a non-decreasing function. It's going to be an increasing function in this case. We're going to get the survival function. And then we're going to get the function that we use to go, if I want to go from probabilities to value on the normal curve, I'm going to use the plot here. And here I'm going to use the inverse survival function for this. So let's take a look, see what happens. All right, so I have the normal distribution. Beautiful, beautiful. And you can see I have a bunch of subplots. The subplots are coming from the subplot aspect and specifying where to put what. And here's the cumulative distribution function. Here's the inverse of the cumulative distribution function. So here we go from values to probabilities. Here we go from probabilities to values. Here's the survival function, and here's the inverse of the survival function. Not too shabby. All right, let's take a look at the density. All right, so here it's a shifted normal distribution. So what we're doing, we have the standard, we have the bell curve, but you'll notice that its mean is at 5 instead of at 0. Standard normal has a mean of 5, and our standard deviation is 2. All right, all right. Let's take a look at random number generation. All right, so what this is doing is I generated 500 data points, and the first one corresponds to a 0 here, then the second one corresponds to a 1 along the x-axis, and then all the way to the right, the 499th observation is going to be over here. And so I can see, are there any trends in my data? We're generating pseudo-random data. We know there's no trends, but this is a good check to see if your techniques of observations and recordings changed over time. All right, now let's do the histogram. And that looks like a bell curve, which it should, because we generated it to look like a bell curve. Let's take a look at multiple normal sample distributions. All right, here we're using a for loop. We're using 2 for loops. So we're going through the number of rows, and we're going to have the range for the number of rows, and we're iterating over all of. So we're iterating from 1 to 5. We're iterating from 1 to 5, and you see I've got a grid going 5 by 5, and we're generating some random values, and then I'm taking the random normal generated values with mean 5, standard deviation 2, and I'm just plotting the histogram. Now I put some tick marks on here, and I'm controlling how wide out, far and left, it's getting displaying. So I'm limiting it to plus or minus 3. When you generate a lot of data, you will get wider and you will get wider values just because. So even if you have the same distribution and I generate 1 million rows or 1 million observations, the axes will have to get wider and wider because I have more observations. More observations means more opportunity for bigger values. So to keep it at a constant size, we go plus or minus 3 standard deviations. And tight layout says don't put in too many margins, kill much of the white space so that we don't get too cramped in the visual. All right, so now here we want to check out the mean of 1,000 normally distributed samples. Let's see what happens. All right, so here we go through and we generate the data, and then we take the mean. All right, so the standard error is 0.2. And that comes from having 100 observations. Square root of 100 is 10. Standard deviation is 2. 2 divided by 10 is 0.2. Boom, that's where we got this. It's not quite 0.2 because of, because it's a randomly generated numbers. All right, now a normality check. And normality check, we want to see, hey, does our data look like it's normal? And so we're generating some fake data. The one that's important is for us to plot. All right, so what I want to do, if it looks like a bell curve real roughly, then I'm like, hey, that looks like a bell curve. I can assume that the distribution of the data is the normal distribution. Then I can use ANOVA. Then I can trust the coefficient tests and linear regression, stuff like that. Now, there's a better way to do this, and that's with a QQ plot. And so what I want to see everything close to the line. All right, this is a little bit of deviation, but that's okay. If I see like a line of dots sticking down or a line of dots sticking this way, I know it's not normally distributed. If it's sticking down this way or up this way, I know it's not normally distributed. The closer it is to the line, the more confidence I have that I'm dealing with the normal distribution. Now we can also do a normal test. Here I can get a p-value. All right, so this test uses skew and kurtosis. This is a method of moments test. Not method of moments. This is a moments test to check to see if we have normally distributed. There are more normal tests than you can shake a stick at. You know, we can also use Shapiro-Wilks. That's the one that one's really sensitive, but it tends to be too sensitive if we have large values. We can also use a Kolmogorov-Smirnov test. That one is kind of coarse, honestly. We only want to use that if we have a large amount of data. And so here, if I have an alpha value, a type 1 risk tolerance of 0.05 with a p-value of 0.15, we fail to reject the null hypothesis. We conclude that, yes, it is normally distributed. Now, something about this is that, remember, we are prone to going with the null hypothesis. And you know, that's just the structure of any hypothesis testing. And in this one, we're saying the null hypothesis is that the data is normally distributed. So I'm prone to saying it is normally distributed. All right, let's generate some more data. Let's figure out the cumulative distribution functions. Let's plot that. Hey, that looks pretty good. All right, so here we're comparing the empirical cumulative distribution function that we get from the pseudo randomly generated data to what mathematically it should be. Those overlap nearly perfectly. It's not perfect, but it's darn close. And so, hey, I have confidence that it's normally distributed. Also, I have confidence because it's norm, you know, I generated it that way. And, you know, we can get the, you know, we can extract percentiles from our cumulative distribution function using this. And we can also use the inverse cumulative distribution function. All right, so if I want to find the 97.5 cutoff, then I need a threshold of 8.92. All right, that's all I've got for you. I hope you're enjoying this material. A little bit of taste of a hypothesis testing. Hope you're doing well and staying healthy.